Okay, I think we'll get started. Um, can I ask everyone to mute their microphones? And I'll do the same once I'm done giving a little intro to everything. So Feng and Sangeeta, do you mind muting? Renju?
Okay.
I'm just hearing feedback as I talk. So, uh, okay. Well, welcome everyone to this session. Reliability and Safety 4 is what it's called. Um, My name is Jonathan Silito from Brigham Young University. I'm going to chair this session. We also have Jonathan Perry here, who just joined us. Jonathan is the student volunteer chair, or whatever, student volunteer for the session. The format for this is going to be pretty simple. We have 6 presentations, and excuse me. So we have 6 presentations. Each one's going to be 5 minutes. So if we keep on time, which we're going to try to be strict about, we should be done in about 30 minutes. At the end of that 30 minutes, we're going to have 30 additional minutes of questions and discussion. So I encourage you to write down your questions or perhaps put them in the chat, because it might have been 30 minutes since you heard the presentation. It could be easy to forget the questions that you had from the earlier presentations. So I think without any further ado, I'm going to invite Sangeeta Day to go ahead with her presentation.
Thank you. Can you see my screen well? Hello?
Yes, we can. Yeah.
Okay. Hello, everyone. My name is Sangeeta Day. I'm a PhD student of Aja University in South Korea. I will talk about our paper, Are We Training with the Right Data? Evaluating Collective Confidence in Training Data Using Dempster-Shafer Theory. This paper is written by me and my advisor, Professor Shilpang Lee. As we know, in the days of AI, training data governs the end behavior of the machine learning model. Therefore, in this work, we argue that we have to understand the training data first. So let's ask, are we working with the right data? Especially for safety critical systems, if the training data is not of good quality, then the results will be unreliable. Therefore, however, in this currently there is no practice of systematic training data fitness assessment before engaging in machine learning training. Therefore, in our work, we try to cover 3 aspects. Firstly, intellectual diversity. That means we want to include diverse experts in the fitness assessment process. Secondly, uncertainty, data uncertainty coming from data representation gap, lack of coverage, bias, etc. And epistemic uncertainty coming from lack of knowledge and disagreement. Finally, the objective is to quantify experts' combined belief on whether the collected data is safe or dependable enough to be used for the training purpose or not. And we use Caltech and JAD datasets for pedestrian detection feature of autonomous cars as running examples. As such, quality assessment is very subjective and does not give binary answers. We try to use Dempster-Shafer theory, which is different than the probability theory. So, for example, traditional probability theory, if we have to ask like who was the killer, we can only express in terms of probability and in terms of singleton set like this. Whereas in case of Dempster-Shafer theory, we can express our belief in events even when we are not sure. For example, we can show our strong belief that yes, Jim is the killer, strong disbelief that Jim is not the killer, and the uncertainty that Jim may be the killer. This is the stepwise method that we propose to evaluate collective confidence in training data. First, we expect that the data expert, machine learning expert, and domain experts will collaborate to understand the sources of data uncertainty and set criteria to minimize their impact, which will look something like this in the context of pedestrian detection, the representation gap, lack of data coverage, what are the criteria. Next, the data will be collected and data expert can perform EDA, that's exploratory data analysis, and collect evidences to related to the claim that uncertainty has been minimized. And then the machine learning component level expert and system level experts, they will individually evaluate each evidence and categorize them as positive, negative, or cannot say. This is the summary of the sheet. I'll not go into detail, but each of the expert can provide their opinion, whether positive, negative, or inconclusive. Finally, we apply Dijkstra-Shepard theory and combine the individual belief masses by Jaeger's rule. So this is a visualization, like when the machine learning based component level expert and system level expert, they evaluate the evidences. Each positive evidence adds on to the belief that the data is safe. Each negative evidence adds on to the belief that data is unsafe, and the uncertain or inconclusive evidence adds on to the uncertainty. As you can see from this, this is the collective belief. This is how we use the Jaeger's rule here. And as you can see, this is not a mere summation of the belief masses only in the safe, but it also considers the belief hidden in the uncertainty window, that is the intersection in that the data is safe. So finally, what we show here in the data, that Caltech dataset, which has been extensively used by many computer vision experts to show the performance of their model. However, it has several lackings regarding the representativeness of the domain variability. Therefore, it shows a significant amount of uncertainty window. Compared to that, the JAB dataset, which is a more diverse dataset, it covers more environmental diversity in poses and accessories. We could collect more positive evidences, and uncertainty window got reduced compared to Caltech dataset. So we finally, to summarize, we assess the fitness of the training data, and we use the Dijkstra-Shepard theory to derive the collective confidence. It can enhance the explainability and traceability. It can also be useful for safety assurance, where data quality can be assured by claims and evidences. We think that recurrence engineering can play an important role here, and we are currently working on multi-layered framework and also working on empirical study. So thank you.
All right, thank you, Sangeeta. Appreciate that presentation, and thanks for being timely. So next up, also from the NEAR track, we have Lance's presentation. Do you want to go ahead and share and get started?
You're muted at the moment.
Sorry, I muted and couldn't get people to confirm that they were seeing my slides. Let me try again. Apologize for that. Okay. How about now? Can people see my slides?
Yes, we can. Nice.
All right. I'm going to get started. So thanks for coming to this talk. I'm just going to get my own timer started just to keep myself on time as well. So this was work performed by one of my former PhD students as one of her present students at the University of Tulsa. And the main idea here is, my background is reliability modeling, so mathematical modeling, but with a focus on software, not hardware or systems. And I find that there's a lot of papers out there on various, types of modern software practices, whether, whatever the word soup of the day happens to be, DevOps, CI/CD, site reliability engineering. So we know these fields like software performance engineering, but we took this definition of DevOps, which is reducing the time to deliver the product while preserving quality, and we tried to transform that into a mathematical model. Long story short, but in doing so, we found that there was a multi-objective problem, and our Markov model basically enabled us to do reinforcement learning. So two of the trade-offs we modeled here explicitly were the trade-off between delivery time and downtime. And of course, we make many simplifying assumptions, but with the interest of trying to get a baseline model on the books, and then we could do data collection in collaboration with folks who do experimental research and hopefully improve the model. Now, here's the interesting thing is there's going to be a trade-off between these objectives. And so the question that comes to mind is, how do we strike that right balance according to the stakeholder needs? And that's, the subject of ongoing research. So as I've said, what we've done is to develop a Markov decision process, and we use fairly standard methods, Q-learning with upper confidence bound. what we've been able to show is that, well, it doesn't match a naive, like say, brute force method of enumerating policies just to see the Pareto curve of the various trade-offs between the two objectives considered. It does come within a factor, and at least we get something on the board and we have something to strive for and improve upon. Let's just look at the model. So here you have this very, very basic three-state model. You have the dev state where there's these developers, there's some notion of incremental deployment, or what the research community has previously called stage rollout, and then there's this notion of an ops state. Each state has a failure rate, and we assume it is monotonically increasing. So in later states, the failure rate will be higher because there's a larger user base. So in some sense, you can think of this as accelerated life testing from reliability engineering, but in the context of software. The two transitions that are the policy we want to learn is how long should we take to transition between the dev and the I state and the I state and the ops. So the trade-off is that we will accelerate the discovery of defects as we transition to these later states more quickly. However, the problem is that we may have more unlucky people because there's a larger user base. They may experience unpleasant things like crashes and hangs, that sort of thing. So there will be this implicit trade-off between downtime and delivery time, because the idea here is we want to remove all the defects and then leave it in operational use. Going back to that popular definition of DevOps of delivering quality without compromising speed, or the other way around. So we didn't have data, so we used traditional failure data. This is time series. Each line on the bar denotes the time at which a defect was discovered in a traditional software failure data set from a monolithic waterfall method. But the idea here is that this is representative of traditional testing, where we find many superficial defects at the beginning, and later on you can see that there's larger gaps in times where there's no defects discovered because of testing. So while other methods might accelerate, or prove to design better tests, what we're looking at is, in the absence of all the other good papers being presented here at the conference, how do we balance these big picture problems? And we go through and we give some numbers, like maybe there's a population of 10,000. That intermediate state has 10% of the users in the incremental deployment state. So not everybody's being subject to the failures, meaning that 1,000 people would be using users would use the product in the intermediate state, even with the defects remaining, and that there are, say, 50 developers. And we make very widely unrealistic assumptions that the developers are just as good as or bad as the other 950 users in the total user base, say, and therefore that we just do the simple ratio of the populations to describe the failure rate transitions back to the dev state. We define delivery time as the time to reach the end of the timeline, that is, find the last defect plus go from the dev state to the op states. And we define downtime as the penalty based on the state we're in at the time a defect is found. So hence we penalize the discovery of defects later in the life cycle. I'm sorry, I know I'm running over, so I'm just going to wrap up. I'll show the results. The standard reinforcement learning is there. We wanted to assess the effectiveness of the learning algorithms. And so what we're showing here is the Pareto curve on the left is the naive approach that just brute forces various pairwise combinations of the policies of transitioning from the dev to the intermediate state and the intermediate state to the dev state. And this is how the reinforcement learning did. So while we didn't match, the second curve could be better. We have a gap and we can improve upon that. So there's lots of room for improvement, and we can discuss more during the open session.
Yeah, thanks, Lance. And we will have time to discuss, so everyone can just remember what they want to ask Lance later. Okay, so next up we have a presentation by Feng Zhu, and this is from the Software Engineering in Practice track. So go ahead, Feng, and share your slides. Or go to presentation mode first and then share.
Can you see my screen?
You can see your screen. There we go. Yeah, that looks good.
Okay. Hello, everyone. My name is Feng Zhu. I'm a software engineer from eBay. Now let me make a brief introduction about our paper, an empirical study on quantity issues of eBay's big data psychoanalytics platform. For enterprises, psychoanalytics platforms are important to decision support and business intelligence. With ever increasing data volume, many organizations started to choose Hadoop ecosystem as their big data solutions for scalability. Meanwhile, a number of new big data circle analytic systems have been proposed and gained popularity, such as Hive and Spark Circle. In eBay, we also have started to build such projects called Camel since 2018. It is based on well-known Spark and follows a typical Circle and Hadoop architecture. In our production deployments, Camel provides services with many Swift servers running in Hadoop cluster. As a fundamental infrastructure of the company, the platform service quality can adversely affect business and user experience. Despite the popularity of the big data circle systems, we found a few studies and service quality issues were carried out for them. According to our daily maintenance activity, we believe it is important to understand the common issues, patterns, and root causes. Therefore, we studied 1,884 tracked issues and tried to answer the 3 following research questions. What are common symptoms of the service quality issues? What are the common root causes of the service quality issues? And what are the efforts researchers can do to mitigate these issues? For the first research question, we found the issue can be manifested as more than 15 main symptoms. The symptoms can be classified into 3 categories: job failure, job slowness, and run results. The most prominent job failure symptoms are IO exceptions and threshold triggered exceptions. For the job slowness, one case is abnormal run running against common sense. Another one is a relative longer time than before. The run results can be incomplete data or incorrect values. In practice, we found some run results may even be identified after several months since they occurred. For the second research question, we found the root causes can be classified into 3 major categories. About 15% issues are caused by user-side faults. About 46% issues are caused by system internal defects in Camel Spark during the query planning and execution phase. And nearly 14% issues are caused by the platform mismatch among different open source components. The second research question is a core part of our paper, and we conduct in-depth analysis and discussions for them. For the third research question, we want to highlight several pain points and lessons learned in our practice, including the lack of circle anti-pattern detector, effective query plan transformation, automatic configuration, efficient data and resource management, and advanced replay and diagnosis tools. To conclude, we perform study on the service quality issues of eBay's Camel platform. We present the symptoms, identify the root causes, and further discuss the lessons learned and insights to motivate future research. Okay, thank you for listening.
Thank you, Feng. So the next 3 presentations we have are from the technical track of the conference. So next up we have, let's see, Jingzhu He. Are you ready, Jingzhu?
Can you see my screen now?
Yes, we can. And we can hear you.
Okay, let's start. Hello, everyone. I'm Jing Zhu from Shanghai Tech University. Today, I will present ProofSeq, extracting performance bug signatures by multimodality causal analysis. Performance bugs are inevitable in cloud systems. They often cause serious service outages. During our empirical study, we observed that many performance bugs repeatedly occur in different versions of cloud systems, which can cause redundant debugging over the same bug. Moreover, microservices use make the bug replication easier than ever, because the same bug can occur in multiple containers that are created from the same container image. Based on the two observations, performance bug signatures can help system operators quickly identify recurrent bugs and provide useful diagnostic information for developers. Previous work on performance bug diagnosis has two major limitations. First, previous work mainly focused on depicting performance bugs over a single data type. Second, the existing tools are not application agnostic. We use a real Hadoop bug to illustrate how a performance bug happens and in machine data. The root cause function of this bug passes 0 timeout value to the configuration incorrectly, and 0 means never timeout. Therefore, when the name node experiences some unexpected problems, outages, the data node hangs on waiting for the response from the name node. We observe that when the bug happens, no anomaly pattern manifests at the data node. Instead, at the name node, log entries produced by server stopping are missing. Even if developers can discover the missing log anomaly pattern at the name node side, it's still difficult for them to pinpoint the root cause, which is located at the data node side. To address this problem, we present PerfSig. When a performance alert is generated, PerfSig is triggered to analyze recent machine data, including system metrics, system logs, and function call traces. For system metrics such as CPU usage, PerfSig adopts low-pass filter to remove random fluctuation brought by workloads. Then, PerfSig leverages signal processing and unsupervised machine learning to identify fine-grained anomaly patterns. For system logs, PerfSig leverages semantics-based grouping, which is word embedding, to classify logs generated by different. Then PerfSig conducts frequent sequence mining to extract log sequences. Then PerfSig uses the log sequences to identify two log anomaly patterns. After anomaly pattern detection, PerfSig performs causal analysis between the anomaly patterns and function call traces using information theory method, which is mutual information. Identify the root cause function, which is the top contributor to the anomaly pattern. Lastly, PerfSig outputs the performance bug signatures as a combination of the detected anomaly pattern and the pinpointed root cause function. We have reproduced 20 real-world performance bugs from 6 commonly used cloud systems. We can say 6 out of 20 reproduced bugs are distributed performance bugs, 15 bugs are hand bugs, and 5 bugs are slowdown bugs. For bugs which have system, PerfSig can identify 3 different anomaly patterns from 11 tested bugs. These numbers are the ranks of root cause functions using causal analysis. We find performs other alternative approaches. For bugs which have log anomalies, PerfSig detects 2 log anomaly patterns from 8 out of 9 bugs. The results show that PerfSig outperforms the alternative log analysis approaches. To conclude, PerfSig is a multi-modality performance bug extraction framework. We have described fine-grained anomaly detection methods to capture manifestation of performance bugs in system metrics and logs. We have conducted causal analysis across different machine data using information theory method. We have evaluated over 20 performance bugs on 6 cloud systems. We can produce precise signatures for 19 out of them. That's all. Thank you for your attention.
Next up, we have Elizabeth Danella.
Okay. Hi, everyone. I'm Elizabeth. I'll present our work on Toga, a neural method for test oracle generation. Unit testing is a standard practice to improve software quality. So consider this unit test, which is testing a stat class. Tests usually consist of two parts. The first being a prefix, which drives the unit under test to some interesting state, and the second being an oracle, which is a description of the expected behavior upon executing that prefix. So the question of what the expected behavior should be is called the test oracle problem. For example, should the stack be empty after pushing and popping, or should pop throw an exception if it's invoked on an empty stack? Historically, some automated test generation tools enforce general safety properties as test oracles. So safety oracles are properties which should be true across all programs and are not specific to a certain program. And safety bugs can find a bug like the unexpected null pointer exception in this example, but they can't test for program-specific functionality like the stack should be empty after a push and pop. So to generate oracles for program-specific functionality, some methods mine the doc strings of programs for user-written specifications. However, we observed in practice that many buggy methods either had vaguely written doc strings or lacked doc strings entirely, and these approaches struggle in these situations. So recently, generative neural models have been used to generate test oracles, and these are appealing as neural methods are more flexible and robust to noisy inputs compared to docstring-dependent approaches, but they have no syntactic guarantees and make many errors in practice. So in this example, the model generates an assertion on the length property of the stack. However, suppose that length is a private member of stack. So current neural methods don't take advantage of these properties and may generate an assertion that does not compile. So our objective in Toga is to utilize the flexibility of neural models while also providing some compile and runtime guarantees. So sequence-to-sequence models struggle as the entire search space of oracles is massive and includes many invalid candidates. However, we observed a common structure in a large corpus of developer-written assertions, and by exploiting this observation, we can restrict the space of oracles that the model can select from, and this makes the model's prediction task much easier. So we formally express this space of oracles that we consider using a grammatical structure based on those observations. And this structure covers both exception oracles as well as assertions. And this space is deliberately restricted, but we found that on a large corpus of developer-written assertions, most do fit this grammar. So our end-to-end approach to generate tests involves generating a prefix from an automated test generator, such as EvoSuite, and then plugging in our Toga-generated oracle to obtain an entire test. So to zoom in on our oracle inference system, so first, Toga takes as input the test prefix generated by some testing tool along with the method under test. And our approach has two models, one for exception inference and one for assertions. And so the exception model is invoked first, and it decides if an exception is expected or not on the given test prefix. So if an exception is expected, then we have an entire test, and we output our oracle in combination with the given test prefix. Now, if an exception is not expected, then we invoke our assertion model. And similarly, our assertion model takes as input the test prefix and the method under test. However, it also takes a set of assertion candidates. And this set of candidates is obtained using our grammar and instantiating the concrete values using values that exist in the prefix and also values that are common across all programs in our training corpus. So to quickly summarize two key results from our evaluation, the first is on, we evaluate our assertion inference accuracy on the ATLAS dataset, and we achieve 69% accuracy over 62 in the unrestricted sequence-to-sequence model. And then secondly, we evaluate our tool's bug finding ability on the defects for J benchmark of real-world bugs. And Toga's generated oracles are able to identify 57 bugs, which is in contrast to the next best performing method, Randup, which employs safety oracles. And so those 20 bugs that Randup find were all exceptional as they were safety oracles, in contrast to our method, which could find both assertion and exceptions. Thank you.
Thank you, Elizabeth. last but not least, we have Renju Lee. Go ahead and share your screen.
So is that everything functional?
Yep, looks good.
Okay. Hi, I'm Renjue Li from the Institute of Software, Chinese Academy of Sciences. My pleasure to share our recent work on neural network robustness analysis. Our title is Towards Practical Robustness Analysis on DNNs based on PAC model learning, and we named the method DPAC. When we talk about the robustness of a deep neural network, we want to study the output of the DNN in the neighborhood of the inputs. In this paper, we analyze the local robustness regarding a single input. So a critical measure is the maximum robustness radius where a DNN can hold its robustness. The problem here is to estimate it. Here, we review some existing methods to estimate the maximum robustness radius. Traditional verification-based methods can hardly satisfy the large DNNs in production. Adversarial attacks have no guarantee on its estimation, while the statistical method is often imprecise due to the huge input space. So, what we do is to solve the problem from the perspective of model learning. Imagine a surrogate model which is extremely similar to the original DNN. If we can verify the robustness of the surrogate model, we may transfer the property to the original DNN. Here, we present our framework. The main idea of our paper is to learn a good enough model which abstracts local behavior about the robustness of the original DNN and then analyze robustness on the learned model. Since we want to estimate the robustness with some guarantee, we must define the meaning of good enough. Here, we bridge the learned model with the original DNN by a probably approximately correct, PAC for short, guarantee. The absolute error between the learned model and the original model is bounded by lambda, with the confidence at least 1 minus eta and the error rate at most epsilon. What we learn here is the score difference function of the original DNN denoted by delta. The score difference function is a good indicator of the robustness. As the score difference is smaller than 0, the model is robust. So we will learn its surrogate, delta prime, under the PAC guarantee using the scenario optimization technique. After learning the surrogate model, we see the original model is PAC model robust if the surrogate model plus the margin lambda is smaller than 0 in the neighborhood B. Since we learned an affine model, so the property can be easily checked. Now we show some of the experiment results in our paper. We first evaluate the 4 methods on MNIST. In most cases, the maximum robustness estimation given by Provero is even larger than the upper bound identified by PGD. In contrast, DPAC estimates the maximum robustness radius more accurately, which falls in between the results from Iran and PGD mostly. Since the range between the estimation of Iran and PGD contains the exact maximum robustness radius, we conclude that DPAC is a more accurate tool than Provero to analyze local robustness of DNNs. We also run DPAC on larger datasets and networks. We test on CIFAR10 ResNets with different parameter settings. We found that the results are relatively stable, and the DPAC shows good tolerance to parameters. The ImageNet experiment shows our framework is efficient and scalable. In future work, we want to improve our framework in multiple aspects, considering more complex input regions, stronger surrogate model templates, and extending DPAC on other properties. For more details and results, please refer to our exit paper. Thank you.
Thank you very much, Renju, and thank you, everyone. So we've just had 6 wonderful talks, and now is the time for us to discuss any questions or comments that people have. Maybe just 2 points of etiquette. It would be great if when you ask a question, you could say your name and where you're from. And also, it would probably be helpful to identify who you're asking the question to. Which paper or which presenter you're asking your question to. So with that, let's just go ahead. Who wants to lead us off with a question?
Yeah, actually, I have a question about the paper that about the I don't TOGA. How to pronunciation the true TOGA is. Yeah. So I think that the author tries to use neural networks to generate some annotations and ranking the annotations using another neural network. Is that correct?
So the candidate list of assertions is generated deterministically through the grammar, and so the model does the ranking. The model doesn't generate the candidates; it selects.
Oh yeah. That's a mistake I made. So actually the question is, what if the assert value is not in the dictionary? Yeah.
So if the assert value is not in the dictionary, then our model will get it incorrect. Like, it won't predict the correct assertion. However, we did some error analysis in our paper on how frequently that occurs. I can't remember the number, but it was a large majority, I believe over 80%. Gabe is also here. Gabe, do you remember the number? Yeah, maybe I can send you the exact details.
Okay. So the case that the value is not in the dictionary is quite few, right?
Yes, that's correct. And the reason for that is that we have 2 different dictionaries, and the first is a local dictionary, which is constructed by grabbing values that actually exist in the prefix. And so that's a really common scenario, that you're going to be asserting on some value that already exists in the prefix.
Yeah. Thank you.
Great, thank you. Other questions? Okay, I have a question. So my question is for Lance. When you showed your model, you said something in your presentation about the assumptions you're making about I think it was the rate of failure, or the probability of failure going down, going up as you iterate through the model. Did I understand that correctly? I wonder if you could just say a little bit where that assumption's coming from.
Right. So, I mean, the main idea is, and it's basically a simple linear assumption that the rate of discovery of defects is proportional to the number of users. So if the earlier states to the left in the model have fewer people doing testing, then the rate of discovery would be proportional to that smaller fraction of the user base. And there's no reason why we need just one intermediate state. One could have multiple intermediate states to somehow progress from left to right, with the rightmost state being the full user base. And of course, that also makes the simplifying assumption that the user base doesn't grow over time. But the main idea is that as more people are playing with the software, somebody's bound to find something that's inconvenient and impacts some subset of that population.
Yeah, that makes sense. Now, one thing I wonder about, though, in that context is what happens, like, assuming you are doing this in multiple stages, so the proportion of the user base is growing.
Right.
Does that assumption still hold, I wonder, because I wonder if some of the defects are already discovered, and so the likelihood of I guess I wonder what happens over time, even though the user base is increasing. You've also been it's been used longer, I don't
Right.
know if that makes sense, but
You're correct. So certainly, you know, so one of my recent PhD graduates did some work in the not just modeling the rate of software defect discovery, but also resolution. So it tends to be a lagging curve. And so certainly there would be that kind of secondary effect of, okay, we know it's out there, we can't totally pull the product, but, you know, so certainly there are lots of opportunities for improvement, both with the quantitative modeling as well as just the data collection to enable that type of modeling. It's something I personally struggle with. I'm always looking for people who have data, would like to collaborate and do more modeling.
yeah, good. That makes sense, though. It does make sense that, yeah, those defects are still there until they're fixed. So
Right.
If
So
you continue the
right.
deployment, yeah.
Right. So just briefly, the original models, they make this they're based on some class of stochastic process. They make a very oversimplifying assumption that defects are instantaneously removed. There are various types of models that have removed that assumption, but, you know, it might be some kind of like what's called a two-stage Erlang process. It's kind of delay between the discovery and the resolution, and it gives rise to these kinds of curves, the lagging curve. So
Yeah, good. That makes sense. Thank you. Other questions? For those of you that would prefer, you're welcome to post your questions in the chat if that's a preferred way to ask a question. Maybe we'll ask Jonathan Jonathan Perry to read out any questions that come in that way.
Can do. I actually have a question of my own as well for Sangeeta, if that's all right.
Please.
All right. You had mentioned in the conclusions the usage on traceability. I was wondering if you could expand the potential usage for traceability.
Yeah, thank you for your question. Actually, what we believe is that when we are talking about collaborations, and then it starts with understanding the data and their uncertainty, the criteria to minimize and to check whether they have been minimized or not. And all along, like currently what we are working on is like having all the artifacts ready layer by layer and phase by phase, and so that we can trace like why we did that, what change we made, or what why we took that decisions, and also who contributed, what is the argument, what is the evidence, what was the claim. So all those things will be more traceable, and we will be able to like find the design rationales from the in the early engineering, even before going for training. And I'm just talking about the data collection part. So currently what we are working on is a layered framework where we can, layer wise, we can talk about like how we understand the problem, how we understand the data, and how we verify the data, and then the traceable artifacts along the journey. So that's how we believe that it will be more, we will be able to explain more about the data quality, the data fitness, and also later on the model. But that is out of the scope. We are just considering the traceability in terms of data related decisions.
Thanks, Sangeeta. Jonathan, did that answer your question?
Yeah, it did. Thank you.
Okay, so in the chat, it says, for Elizabeth, I'm curious, what are the next steps for your research?
Yeah, so the largest limitation of our work is that we trained on developer-written tests, and so that was developer-written prefixes and developer-written assertions. But you notice that at inference time, we're plugging in an EvoSuite generated prefix. And so that's quite the difference in distribution. So probably the most important next steps will be to generate a training data set of prefix oracle pairs, large scale, through some of these test generation tools. Whether that's EvoSuite or Randup or some other prefix generator is still an open question. But yeah, a large scale data set of automatically generated tests.
Thank you. Also from the chat, my question is for Sangeeta. Do all samples need to be annotated? Are there particular samples which are most valuable to annotate?
Yeah, in this work currently we didn't mention that which ones are most valuable ones. It depends on the data type, it depends on the problem domain. But like I said, in the paper, we mentioned that if there is any particular property that needs to be annotated, then that should be given more weightage and more priority, so that our calculation of the collective confidence will be adjusted based on that. So it is not like required like every sample needs to be annotated, or every feature needs to be annotated, but we are talking about the safety critical ones, the corner ones, so that needs to be taken care of. But again, it depends on the expertise of the experts that are involved, so they will guide us on what we need to annotate. If that is very critical, that definitely should be annotated, and we need to check again whether the data actually followed and met the criteria or not, and also given quality based given weightage based on that.
Great, thank you.
Thank you.
So I have a question. Let's go first to the chat before I ask my question. So for Jingzhu, do you have a sense of why PerfSig outperforms related methods? Are there specific parts of PerfSig that are different from other methods in your evaluation?
Sorry, are you asking what are the alternative approaches using in my evaluation?
So I think the question is, I think it's two parts. So what is it about your approach that makes it better than other approaches? Is that a fair, Gabriel, is that a fair?
Yes, sir. I can just ask over.
Okay, please.
Yeah, so that's exactly right. I was just curious, what is it about your approach that you think allows it to perform better when it's doing this this root cause analysis for bugs?
Okay, so first, to the best of our knowledge, the performance bug signature is quite new. So we cannot find much existing work focuses on this part. So and also much existing work focuses on single data type analysis. But we are doing multiple data type, multi-modality data analysis, because bugs can manifest in multiple data types. So for the alternative approaches, we separate it into two parts. The first is for the bugs which manifest as system metric anomaly, and the other part is the bugs manifest as log anomalies. For the metric anomalies, so we implement the alternative approaches to predict the causality. So basically for causal analysis, so implement the correlation-based method like the Pearson and Spellman coefficient. And we find that the mutual information can outperform those approaches. The rationale is that we, the mutual information can capture the nonlinear causality, so it can perform better than the alternative approaches. Besides that, we compare the methods with and without filter. So remember that we use a low-pass filter to remove the random fluctuation. So we can see that no matter which causality, which causal analysis we are using, but we can see that using filter is better than without filter. And then for the bugs which manifest as system log anomalies, we just implement a set of alternative approaches to replace some parts of our approach. For example, we use a word embedding. So we just replace this part with like TF-IDF method to capture, to extract the feature vectors. And the other part is that we use the clustering method because we want to group the log entries which are generated from different tasks together. So to replace with our SOM clustering method, we use like the dbScan clustering, and it's a distance-based method, and it's called other work. And we find that our approach outperforms the other approaches because of like two aspects. The first is that the SOM clustering is better than DBSCAN because SOM clustering can high-dimensional vectors because of the curse of dimensionality. And the second aspect is word embedding is better than TF-IDF because we can capture the semantics. You know that the systems are commonly written by the human languages, so we can capture the semantics to better represent the feature vectors. So.
Great. Gabe, did you have any follow-up, Gabriel? Any thoughts on that?
No, that's very cool. A very good explanation. Thank you.
Yeah, thanks, Jingzhu.
Okay.
Other questions people want to ask?
I have.
Okay, please go ahead.
So I have nice knowledge in testing research area. I'm just curious that is Toga specific to Java, or can it be extended to other languages, or even Java-based languages like Scala?
Yeah, so that's a good question. Our underlying pre-trained language model was CodeBERT, which is multilingual. However, our training data set was entirely Java. We have not tried zero-shot on other languages. I imagine it would perform much worse than it does on Java due to the training data bias, but I could see it working in some cases.
Oh, okay, thank you.
I just also want to say that nothing about the approach is inherent to Java. It's just the data set that we trained our technique on.
Great, thank you. So Feng, I have a question for you, Feng Zhu. At the end of your presentation, you mentioned that one of your contributions is some ideas or some thoughts about directions for future research. I'm wondering if you would take a minute and tell us a little bit about what you think some of the most important future directions could be.
Oh, okay. From a software engineer's perspective, in practice, we found conditions. Address the root causes. Cluster performance issue occurred. We found we always need to analyze the logs and query all these logs to get the root causes. It involves not plenty of major efforts. So we just want to automate this process. In our sorry for my English. The network seems not stable. In our daily work, we found the problem concentrates on several areas. It is the performance troubleshooting. Performance issue troubleshooting, as Jingzhu's slide perfect details. The other is the configuration. We do not have any configuration tools. For in the database area, we lack of some tools like SQL anti-pattern detector. So in the end of my presentation, I just came up with several research areas want to handle these problems to facilitate our daily work.
Good, thank you. Other questions? We probably have time for maybe Two more. So I have a question for Jing Zhu. I'm gonna mute you, Feng. I think that's okay. Okay, Jing Zhu. So one question I had: the data you're using for your analysis, is it data that's collected from the application running in production, or is it expected to be run in other contexts? Like, are you able to get enough data from a production system? Let me know if that question makes sense.
Oh, I get it. So it's a good question. So we do the data collection in the production environment. We have 3 data collection tools, which are system metric collection. So we can do like a lot of tools can do things like that to sample the the CPU usage, the memory usage, something like that. And the second is we have some log utilities to collect the system logs. Still, it's quite easy. And the next part is we do the function call tracing. So I think maybe your focus is that the is quite expensive. It's not applicable in production environments. So here we use the Google's DAPA framework for function call tracing. So specifically, we find that performance bugs often manifest in a subset of the functions. So which means we do not need to trace all the functions in the system software. Instead, we can trace some error-prone functions. So Google's DAPA framework can support such kind of things. So we use various implementations of the DAPA tracing framework. Like for Hadoop system, we use the htrace. For Cassandra system, we use the Zipkin. So, and then we can do the error-prone function call tracing.
Very interesting. All right, thank you.
Thank you for your question.
Okay, who would like to have the last word? Who wants to ask the last question? Okay, well, I think we've covered everyone's questions. So thank you, everyone. Thank you, presenters. Thank you for everyone else for attending. And I hope you enjoy the rest of the virtual conference.
Thanks, John.
Take care.
Thanks all.
Thank you. Bye.